Yeah. So I guess I'm chairing this talk. I don't know. So it's my pleasure to introduce Konstantin Korovin. He's going to talk about the kind of research he's been doing since 2003, I believe, into two calculi for first-order logic. One is called superposition, the other one is called instantiation, and they're connected in some sense.
Okay.
Or not, I don't know. You're going to tell us.
Basically, superposition is a classical calculus for first-order logic. It's developed by many people and still currently it's the most powerful calculus for first-order logic. So I thought it will be useful to introduce you here to you. And I will be also talking about instantiation theorem proving what I'm more working on. Okay, so what is the problem we try to solve? And so problem is as follows. So we're doing theorem proving in first-order logic. So giving a first-order formula, we want to show that this formula is a theorem. Yes. For example, if you have group theory, yes, we can axiomatize groups. So here is axioms for group theory, and we can ask the prove that in all group where each element is of order 3, and in all such groups, this commutator equation holds. Okay. And theorem provers are very efficient to solve such type of problems. Okay, so why first-order logic? First of all, first-order logic is very expressive, so basically you can formalize all mathematics in first-order logic. Yes. And it's also complete. There is also complete calculus for first-order logic, and this means that we can have uniform reasoning methods for different domains, but the reasoning methods are uniform, in particular, for example, superposition, calculus, resolution, or instantiation. Since we have these uniform reasoning methods, then there are also lots of development in designing very efficient algorithms and data structures to reason with these calculus. So it provides good balance between expressivity and efficiency. And there are also reductions like by Jasmine and Joseph and so on to translate high-order logic or problems from ITP into first-order logic. So I think first-order logic provides very good balance between expressivity and efficiency.
So what is the intuition behind your nice cartoon?
Yes, so the intuition is this would be like SAT and SAT. This would be first-order, this would be high-order, so they will consume each other. Yes.
They're like Russian dolls.
Very vicious Russian dolls.
The Russian mafia.
Russian mafia.
It's a Russian doll.
It's a real Russian doll. Okay, so of course there are many skepticism about why these generic uniform reasoning methods will be efficient for just such complicated problems like mathematics and so on. But I think the case in hand, for example, SAT solvers, yes, and in previous week we saw talks that shows SAT solvers were used to solve open mathematical problems, yes, like Pythagorean triples or Euler discrepancy problem, yes. And if you look back to like 30 years ago, no one will, I think people would say that it's crazy that you even try to solve such problems using such a generic method as a SAT solver, yes. And yeah. And I think these generic methods can be used to solve problems in many diverse domains, yes. And we can optimize, so it's the same method, so we can well optimize it.
I have a question or a comment, but if you prefer to take them at the end, you choose.
No, please.
Okay. So sometimes I think that first-order logic is at the sweet spot and so on, which is what you suggest here. But sometimes I think it's at an anti-sweet spot, because this is where you lose this ability, and yet don't have the convenience of higher-order logic, for example. What's your feeling?
This ability is, I mean, it's depending how you look at it. Yes, I don't see this ability as a big issue. First of all, there are lots of decidable fragments that can be solved by this method. Yes, and actually, I can't go into detail here, but many fragments were shown to be decidable by complicated model theoretic arguments. Yes, but later it was discovered that a simple ordering superposition just decides.
Mm-hmm.
And again, this proves the point about universality of this method. Yes, so there is no reason to believe in the effectiveness of this method. Why this generic calculus will decide this fragment that was proven to be decidable by some complicated model theoretic argument, but it is. So, and there is a quote that it's the unreasonable effectiveness of mathematics in natural sciences. I think there is might be also unreasonable effectiveness of such generic calculus to solve general problems. Yes. So there is no objective reason to believe, but that's what happens in real life. So I try to boil down what is basic ideas behind automated reasoning, and it's very related to Kapor's talk. And I think they boil down into three key points. First, we reduce semantic problems to symbolic computation. For example, in groups, we try to solve problem for groups, yes. And groups can be uncountable or whatever. And we try to apply some symbolic method to solve over all groups. So this reducing semantic problem to symbolic computation. Second is normalization, yes. So we will try to normalize our problem such that problem can be solved by trivial checks. For example, in the case of job numbers, the trivial check is 0 equals to 1. And so if your polynomial reduced to a number which is different from 0, so obviously, yeah, so the system is inconsistent. So in the case of logic, it will be, for example, two terms are syntactically equal. In the case of unsatisfiability checking, it can be that you derive the empty clause. So you normalize a problem such that the problem becomes trivial. And the third, this usually is not possible. You need to complete the theory, yes. And this is done when normalization fails. Okay? So I know you go through these three steps in the case of equational logic. So here's the problem. We have some equational theory, like group theory before, and here's a problem from algebra called word problem. Decide that this group theory problem entails this equation. And this is a pretty difficult problem in general, so this problem is undecidable in general, and so on. So first step is to reduce this semantic to symbolic, yes, or syntactic problem. And symbolic reduction is based on the following rule. It's called perambulation. And this rule actually goes back to Leibniz. It basically says replace equals by equals. So, so here, if you take a look at this rule, so we have that S equals to T, and sigma is just matching substitution. It means that there is a subterm which match in this U that matches this S. Yes. And we replace the subterm by this term T. So we replace the equals by equals. Yes. And we obtain new equation. That's it. So this rule called perambulation, and as I said, it goes back to Leibniz and so on. And what is the connection between semantic and symbolic? So it's given by Birchhoff's theorem, but it can be proven in many other ways. So it basically says that this equation semantically entailed by our set of equations, like group theory, if and only if there is a sequence of these applications of this rule, which gives us syntactic identity at the end. So these two terms will be syntactically identical.
Maybe I'll be nitpicking, but do you want to have U and V replaced by S and T of there, or in the second line of where you wrote word problem? No, higher.
What?
This,
U?
what is the link between U and V and S and T?
There's no relation, yes. For example, in this group problem, yes. So we have these axioms of groups. If you scolemize this, it will be some constants and it's just equation.
So
there is no necessarily relation.
S is T is the x squared, x cubed.
So yeah, so the
okay.
So this is x cubed inversely quantified. If you want to go into detail, this would be scolemized, so it will be constants, this x and y. So it's not necessarily, there is obviously a relation because you want to solve this equation in group theory and so on.
Okay.
But it's not, this is the equation we want to prove. Yes. Or you want to prove that, so if you have like group theory and some other condition, you want to prove that the group is commutative. Yes. The equation will be for all x, y equals yx. Yes. So obviously there is a relation, but this equation is not necessarily in the our synthetization.
Okay, thank you.
Okay, but that's what we want to prove, that this, for example, that the group is commutative. Yeah? So we want to prove that x, y equals yx.
In principle, you could also be given several such equations, right? S equals T. Is it?
Here it's many, yes, like in group theory you have 3, yes, but generally it can be any set of equations, or like we later will go into, I really need to speed up. Okay. Okay,
So
so,
the second line just means word problem, check E entails this.
But they're given an equation, right, we should ignore it, because E
Yes.
already has n
Yes.
equations in it, so we don't
Yes.
need an n plus first equation to complete it, right?
no, but, so like in group theory, obviously you can edit,
No, but
so you okay.
Yeah, I think everyone understands.
Yes, but so in group theory here, so is this axiomatization, yes, but here the identity you want to prove, they have different a bit semantic meaning, yes. So obviously you can translate them back and forwards, but here's axioms, and technically they'll be universally axiomatized. This technically will be existentially quantified if you move it to the left.
I think people are confused by the fact that you have general axioms and then you have antecedent of the thing you want to prove. So they are saying that you could add the equation S equals C. to the
Okay, so
axiom.
ST, yeah, okay, this is a good point. So ST is from the from this E, and here's a derived equation from this from the right hand side. Okay, so in other words, you want to check. So this theorem allows us to reduce problem from like class of structures like groups, which can be uncountable and so on, to specific structures called term algebras. And so what we want to show basically is that 2 terms are the same in a congruence class generated by this equality. Yes. So basically what we want to show, we have terms, set of terms, and this is E will generate congruence classes, so which in particular equivalence classes. Now what to show, if you given 2 terms, we want to show that there is a path, which now looks like homotopy type theory. Yes, so there is a path like this, T to S in this congruence. If you can show that there is a path based on these substitutions, then you prove that they're equal, and that's it. Yes. If you can show that there is no path, you can prove that they're different. Okay? Good. So the main problem here is that these classes are generally infinite, yes, so they're not finite. And this is the main issue. So like in groups and so on, this will be basically absolutely free group, yes, and these things are infinite in general. Okay, and here's the idea is that, and it's also very inefficient to apply in all directions this equality, and the general idea is to break the symmetry between equations and use this replacement in one direction. So that's called term rewriting. Yes, so instead of having a set of equations, we have a set of term rewriting rules. So now, and this is the second point, as I said, 3 points. So now we're going to this normalize point, yes. And what we will do, we'll normalize terms based on this term rewriting, yes. So if you have to check that our set of equations imply this identity, we basically want to normalize S and T and obtain some normal form, yes, and if its normal form is the same, basically we try to do it like this, and U. So if normal form is the same, that's it. So this is a syntactic check at the end. So if normal form of 2 terms is the same, they're equal in the same congruence class. Okay. So there are 2. So generally it won't be the case for just if you orient equations. So there are 2 conditions on this writing relation to obtain a unique normal form. And these 2 conditions are this this relation should be well founded. That's Deepak also mentioned. And this is the same idea applied to Buckeberg algorithm and so on, computing Grobnier biases. And this is usually done by using so-called simplification orderings. So the range of simplification orderings like Knut-Bendix, L2R, RPO. And if there is well-founded ordering which corresponds like this, so we can prove that left-hand side is greater than right-hand side, and this is a well-founded ordering, and on top of this it's a reduction ordering, then all our rights will terminate.
What is LPO, RPO?
So LPO is lexicographic path ordering, recursive path ordering. This is orderings which are used to show the termination of such things. So a long time ago, together with Andrei Vorontkov, we showed, for example, that there are lots of interesting computational problems related to these orderings, how to choose them. And like long time ago, we showed that there is a polynomial time algorithm to check whether there exists Knut-Bendix ordering such that orients your term writing system in the correct order, or orients even set of equations. Okay, so this is one ingredient, and another ingredient is confluence. So in order to achieve these unique forms.
Are there similar algorithms for LPO and RPO?
Yes. So for LPO it was shown NP-complete problem. Yes. Whereas for Knut-Bendix we showed that it is polynomial.
And are there some relaxed versions of that? Like if you want only one of those, etc.
Only.
If you want to maximize the number of things you orient, but you don't force all equations to be oriented.
Let's discuss. I mean, this is tiny part of my talk. 1% of my talk. So let's move on and discuss offline. And another ingredient is confluence. Yes. Okay. So confluence is this thing. So what we want to achieve is that if you start rewriting in one direction and start rewriting in another direction, then you can always join it. And the thing is that this confluence condition can be relaxed if you have these well-founded orderings to local confluence and so on. But the fact is that usually if you orient equations, they will be not confluent, yes? And so you get stuck. And that's where we have the third ingredient, which is called completion. Yes? And in case of Knut-Bendix completion, I think it can be boiled down to just application of these two rules. Usually it's formulated much more, how to say, there's many more rules, but I think that should suffice. And basically, here's the idea. So we apply order permodulation between equations in our theory, so in E, so both sides now in E. But we replace only bigger terms by smaller terms. So we replace only if this equation is orientable in the way that left-hand side is bigger in our orderings than right-hand side. And the idea is that we try to reduce our terms into smaller terms. So we generate, so this would be, in Knut-Bendix terms, it would be critical pairs. Yes. And the second rule is demodulation, and that's where we normalize and simplify things. And demodulation allows us to remove certain equations, and certain equations if this substitution is matching. So if it's a matching, we can rewrite to this, and we can forget about this top equation.
But I don't understand what is happening in this rule.
Okay, which one?
The second one, the demodulation rule.
Yes, demodulation rule. So it's sort of similar to this rule. The only thing is that this substitution
isn't there.
Okay, so there is no condition. So okay, I didn't write the condition on the substitution, but this substitution is matching here. So here is a unification, yes, and here is we use matching.
Should it really be U at the end?
Oh, it should be an S, right?
Yes, and S for you. Yes, you're right. So
S
Oh,
and
I'll ask-
R, I guess S.
this should be.
R is
I copied from
S and U.
from the previous one.
Can you write it
You're
on the
absolutely
board?
right. Yes, that's good catch. I was modifying the slides.
It's like
And
USSR.
you chose the notation wrong. So here should be S, yes, and here should be R. Yes, so it will be S, R, C.
Can you write it down on the
Sure.
But it's like the previous one. It's
Yeah,
the
just
one
the
above.
previous one,
Yeah,
but only
like
the
changing what needs to be changed.
Okay, yeah.
Oh, no,
So
it's
modifying it last moment to the slides. So if you have an occurrence,
USSR.
I knew something was wrong. T, then it will be S, equals T,
Okay.
sigma, yes.
Okay.
And this sigma is a matching substitution, yes. So it's there in the first rule, it's a most general unifier, and here's a matching. That's why we can remove this top equation.
But it's just what we would think of as normal directed rewriting.
Yes, but yeah, demolition is just writing. But usually Knut-Bendix completion is presented with many rules and much more complicated, which is fair enough with joining pairs and so on. But I think it also can be presented in a simple way like this. But anyway, it doesn't matter.
Very nice.
So what Knut Bendick showed is that if completion terminates with orientable equations, then the resulting term writing system is convergent. Yes. So it's confluent and terminating. So we can always find normal terms, and therefore word problem for such systems is decidable. And in particular for group theory, they showed that there is a converging term writing system corresponding finite converging term writing system corresponding to group theory, which consists of 10 rules, which are not obvious if you look at them. But Knut Bendick's completion can fail, and like 3 main reasons is that it can not necessarily terminate. It might generate equations that are not orientable. For example, commutativity will be never orientable by any order. And it's applicable only for unit equalities. Yes, it's very restricted class of problems.
Wait, you said that this was decidable class?
For word problems in groups,
No, the Knut Bendick. You said on the previous slide that this was able to decide whether or not there exists a Knut Bendick completion.
No. So in previous, it was whether there exists an ordering that orients term writing system, but it doesn't mean that there exists completion. So orienting just fixed term writing system is different from orienting the completion.
So orienting is related to the termination problem,
Yes, but
and completion is related to the confluence problem.
yes.
I think what's confusing is that Knut Bendick's means 2 things. There's a Knut Bendick's order, which is what was meant on the previous slide, and then there's Knut Bendick's completion, which are 2 different things. The 2 were introduced in the same paper by the same people, but they're 2 different concepts.
Yeah, so they used for the same method. This ordering can be Knut Bendick's ordering here. But anyway, so there are three cases when it can fail because of non-termination. So, and in fact, the word problem is not undecidable in general. So generation of non-orientable equations, like some equations like commutativity, cannot be oriented by any ordering, and it only applied to restricted class of problems, okay, to unit equalities. So superposition is the calculator which extends this idea of completion and normalization to more general logic, which is basically, so this is the main superposition rule, so it looks horrible, but the basic idea is exactly the same. So it goes back to the perambulation, but now applied to clauses as well. Yes. And the idea is here that although we cannot always reach this convergent term writing system after finite number of steps, we can do it in the limit. Yes. And so this superposition calculus tries to achieve confluent and terminating term writing system in the limit, and shown that it's always possible. Yes. So in the limit, what you will obtain, it's a convergent term writing system, but due to obvious undecidability, first of logic and so on, this can be so the best result you can hope for.
So how many rules will be there? How many rules are there then?
So here's 3 main rules, yes, for completeness. So superposition is the main rule that corresponds to this ordered perambulation, but extended to.
Can you put it all and
Yeah.
give us time to look at it?
Yeah, but that's not the purpose of this talk.
Doesn't this give a decision procedure for the word problem for groups? Doesn't this give why doesn't this give a decision procedure for the word problem for groups? Because if in the limited it becomes decidable, then can't you solve a word problem just by adding more and more?
Yeah, sure. It gives you semi-decision procedure, yes. For any word problem, for groups, it will terminate and it will give you decision procedure, yes. For all groups, for the class of all groups, yes. But again, so there are groups for which word problem is undecidable, yes, even finite representative groups. But what I'm talking about, the class of all groups, yes, and the problem for the class of all groups is simpler than the problem for the class of some specific groups, yes. Okay. Okay, so but this is again tiny part of the talk. Okay. Good. So that's it. Yes. So this is actually was my introduction to superposition calculus. Yes. And so the basic idea is the extension of this Knoop-Benedict completion idea procedure, but now we obtain this convergent term writing system in the limit rather than hope for final termination. And Bachmann and Gansinger showed that this procedure complete first order logic. So currently most powerful theorem proofs for first order logic that based on this superposition calculus. Nevertheless, there are some weaknesses in this approach. Yes. And resolution rule is basically a special case of superposition where we have, you can see this resolvent. Yeah, so basically, if you want, I can show that it's just a special case of superposition. But nevertheless, resolution is also complete for first order logic, but less efficient for when you reason with the properties. So, but nevertheless, resolution has weaknesses, and here's like, for example, it's not efficient in propositional case. You would hope that since first order logic extends propositional logic, then the method for first order logic should be as efficient as current method for propositional logic, and it's radically not the case here, because if you apply this resolution rule to propositional logic, usually it's not a good idea by itself. So such solvers are based on TPLL and CDCL. So lengths of clauses can grow fast. So you can see here, if you resolve this and this clause of n and this clause of m, so this will be, they can double, yes, at each step, and you need to apply to repeatedly this rule, so you can see that it's very quickly can will grow very fast. There is also another problem, so-called recombination of clauses. So the same reasoning as you do here and here, after adding this clause, you might repeat on this part of the clause. Yes. So these clauses are not removed; they added usually to this iteration procedure, and therefore the same reasoning can be repeated many times. And there is no effective model representation. So if you're interested in counterexample, then resolution might be not very good, and superposition might be not very good. What it gives at the end is a situated set of clauses, so bunch set of clauses that theory shows that it's convergent, but it's very difficult to extract any reasonable model representation from that.
What would you mean by reasonable model representation? If it's infinite, like would you have anything which is more reasonable than
for example, like in this instantiation approach, I have representation in definitional extension of germ algebra, yes, and this is decidable and so on. Whereas here, representation is basically not decidable. It's not. It just says that this bunch of set of clauses terminated based on many conditions of my inference rules, and these completeness theorems have a theoretical result. It must have a model, yes. But how this model looks like, no one knows. Okay. So this is come to this instantiation idea, and basic idea is, can we approximate first order reasoning by propositional or ground reasoning? And here's the idea that can we use these efficient SAT solvers or SMT solvers to sort of drive this first order reasoning? And the answer is yes, and it goes back to Herbert and so on, that if you have quantify free formula, then for all x is unsatisfiable if and only if already some ground instantiations of this form is unsatisfiable. And this idea is goes back to the regions of theorem proving in first order logic, and any of such procedures are based on this Herbert theorem, and even resolution itself also can be seen based on Herbert theorem. And there are many more new developments here. Yes. So what we were looking at with Harald Gansinger on this GEM procedure. So there are two approaches here. First is to extend efficient methods for propositional logic like DPLL or CDCL into first order logic. So they lifted this calculus, and it's turned out to be very difficult. Yes. And so far I haven't seen a really like so there was this implementation of model evolution calculus, which is based on this idea, which was pretty good, but yeah, still had really lots of difficulties, I think, in the sense that calculus become very complicated and it was difficult to implement. There is new approach also by Maria Paola and Plaisted. Yes, but again, so from implementation point of view, I think it's a very difficult approaches. So what we did is to get a modular approach where you can separate first order and propositional reasoning and use propositional solver as a black box. So here's how it works. So we start with a set of first order clauses, and we want to approximate these first order clauses by propositional reasoning. And we're just doing it very simply. We ground all clauses by just one designated constant, which we call bottom constant. Yes. And in this case, if you do this, we replace all variables by constants, we obtain ground clause, set of ground clauses. Okay? Good. So now we have a set of ground clauses, we can apply SAT solver. And SAT solver, if it returns unsat, then theorem is proved. Yes. And obviously, it doesn't mean that it is satisfiable in first order case, because there might be some other instances which lead to unsatisfiability. So what we'll do, we'll take a look at the model of this propositional set of clauses, and we'll try to analyze why this model cannot be extended to first order model. Okay? And it turns out this propositional model cannot be extended to first order model if and only if there are two complementary literals which are different from the SAT point of view, but they're unifiable in the first order case. Okay, and what we can do, we basically resolve this conflict by instantiating these clauses by this most general unifier based on this model guidance. And we add these instances to our set of clauses and repeat the procedure. And we showed a long time ago that this procedure is sound and complete for first order logic. Yes. And nice feature of this procedure is that it utilizes SAT source as a black box, and it also guided by SAT source. Yes. So it's guided by the models returned by SAT source. Okay, so let us compare these to just inference systems. So resolution and instantiation. So they look similar. So we have here resolving a literal and obtain this, and here we instantiate two clauses, yes, by similar type. But they also are quite different. First of all, since it's integrated modular ground reasoning is as efficient as you like in the ground level. Yes, if the problem is ground, it will be just SAT solving. The length of clauses is fixed, so they never recombine or never grow. There is no recombination of clauses. There is also semantic selection. Here, selection is based on orderings, and these orderings are fixed usually from the start of the procedure, whereas here, the selection is dynamically changed by the SAT solver. We showed that there are lots of powerful redundancy elimination, which is relevant to this instantiation procedure. And also have this effective model representation. So after after this procedure terminates, we can extract the model. Yeah.
So what's your selection if you have a non-determinacy in choosing what result?
Yeah. So and this procedure allows you quite big flexibility. So there are many, in the same clause, there can be many literals that are true in our model, yes, and we can pick, so the series tells us we can pick arbitrary, yes. So in implementation, there are lots of heuristics how to pick this arbitrary.
So it's similar to given clause selection.
No, but we're not selecting clauses, we select literals within clauses.
Yeah.
Yes, where it's not allowed by superposition.
I mean,
yes, so heuristics can be, yes, like whether it's positive, negative, number of occurrences of symbols, whatever, whether it's ground, number of variables, this type of heuristics which can be combined lexicographically and so on, so in the implementation.
So all the wording you use means that you are using a certificate coming from the SAT solver, which is the certifying model.
Yes.
And you are producing a certificate for your users also, based on the unifier.
Yeah. Okay. So at the end we can produce proof. If you obtain a proof, it will be grounds. So it's basically a collection of instances of your original problem. Yes. And this problem will be a proposition unsatisfiable. Okay.
So This step here is you're using a particular substitution, right?
Yes, it's most
And,
general.
and it is it could be any substitution, or is the least substitution
Most general unified.
Then it's the same as superposition. Wait, what am I missing?
No. We don't.
Oh, you
use
don't
this
generate the
usually.
clause.
Yes, but this is, it looks like the same, but it's big difference, yes. So these two clauses are not recombined, yes. So the length, for example, the length of the clauses stay fixed. And in particular, this is a decision procedure for so-called EPR fragment where the resolution is not, yes. And this gives quite a lot of difference in the calculus. So basically, instead of resolving ourselves, we let SAT solver to decide whether to resolve or to do whatever it likes with this instance, yes.
So
And
how
usually,
how do you extend the results on redundancy in the superposition calculus with this?
we do model construction, we just do it from scratch, and we do model construction based on so-called closures, yes. And instead of considering clauses, we use closures, and then we make ordering on closures, and do model construction on closures, and then redundancy, the specific redundancy based on this
Or
closure.
does that not require a lot of bookkeeping?
For the proof, or for the
No, for
implementation?
when you're trying to generate a proof, yes. For at least for a redundancy check.
No. It's, you can, based on this theoretical result, you can justify lots of redundancies. Similar like in superposition, you can justify like subsumption and so on. You don't need to bookkeep how this redundancy is justified.
Just one thing, a question about do you replace the clauses theorem, or do you just add these new clauses?
Add. You cannot replace, yes. Because this is instances, yes. And in later, this can be unified again with something else and so on. So you cannot just replace them, unfortunately.
Can I do one more?
I haven't yet started talking.
There is also non-determinacy in the solver's model, right? Like if you run different solvers using different heuristics, you will get different.
Yeah. So this is advantage you might think is disadvantage, but I think it's advantage because it's dynamic. The selection is during the proof search, this model changes, yes. And based on the new instances, this model is repairing, yes. Basically, when you add these two instances, these two literals are prepositionally equal. So SAT solver knows that they're complementary, yes. And so in the next run, it will need to select something different here, and so on. So it repairs the model. And repairs this model towards first of the model.
I hate to do this, but see, like sigma, you said is most general unified, so it's not a ground substitution.
No. That's also the advantage of this compared to others, that we don't need to use ground substitution, we use model.
But then how do you invoke such SAT solver?
So we again substitute late after that, we just substitute by one constant.
Oh, that's where the instantiation comes.
Yeah. Okay.
Yeah, 5 minutes and then.
Okay. So basically, yeah. So this is implemented in iPro, yes. So, but this is like instantiation-based loop, which is similar to given clause algorithm in superposition, but there are lots of differences as well. And basically, this given clause algorithm take an input set of clauses, pre-process it, submit some groundings to SAT solver. Then submit clauses to passive queues. Yes, so ordering clauses are ordered to with some heuristics. Then from this passive queue we take a clause, yes, and we perform all inferences with so-called active clauses. So set of active clauses is the set of clauses with which all inferences are already performed, and so on. So the most expensive parts are here simplifications. There are lots of indexing techniques and so on going here. So overall, it becomes pretty extensive implementation. Okay. So this again, all this was implemented in iPro, yes. And so iPro instantiation-based theorem proof of first order logic, which is based on this calculus, but also combines resolution. So proof search is guided by SAT solver. There are lots of redundancy elimination. For example, global subsumption is an interesting redundancy elimination, which allows you to simplify first order clauses using SAT solver. So although SAT solver just see these propositional abstractions, it still can be used to simplify full first order clauses. Mismatching constraints, and these mismatching constraints are instantiation specific, redundancy elimination, also very powerful. Predicate elimination, so this is, I used it as a pre-processing technique, but it's, so predicate elimination, symbol elimination, and elimination like in Grobner base is all related. So that's how you eliminate symbols, and in this case you eliminate predicates. Semantic filtering, splitting, and so on. So lots of indexing techniques for inference and simplifications, sorted inferences, so I infer sorts. So even if initial problem is unsorted, it's possible to infer sorts for this. And so-called non-cyclic sorts. That's and this non-cyclic sorts allows you to efficient for more efficient reasoning if you detect them. So finite model finding. Again, this method is very good for finite model finding and based on translation into the EPR and based on sort inference and this non-cyclic sort inference. Then I try to work on some applications of this theorem proving procedure. So to bounded model checking, K induction, QBF, solving bit vectors, planning, query answering, and so on. And work on some proof and model representation. And proof becomes non-trivial through these global simplifications.
You had some follow-up papers for where you support equality, right, on the ECC chain. Is I proven implementing the follow-up?
So this will be the next. So this is the next slide. So yeah, so this is all without equality. So back to superposition. So if you would like to extend this calculus with equality, and you can try it the same idea. So this is superposition calculus, and it has the same weaknesses as resolution. So it's not efficient in ground case. The length of glosses can grow even faster because now you can replace every subterm by some new subterm, but you need to drag all side conditions. Yes. So if you have a huge term and every position in the term can be replaced by another term, so you need to copy these side conditions everywhere, and they will be growing at each step. So lengths of glosses growing, there is a combination, no explicit model representation. So what about superposition? Applies the same idea as superposition instantiation. So we have like this, and now instead of superposing, we just instantiate this and here with the same unifier. Okay, so this would be not complete. For example, if you have this set of equalities, yes, there is no non-trivial instantiation here between these terms. Yes. So basically, you're stuck. So instantiation is not applicable directly. But what we did is to observe that if you apply proof, apply unit superposition to this set of equalities, you obtain a proof. And from this proof, you can extract substitutions. So you trace back this proof, and you can propagate these substitutions back from the proof to the original problem. Yes. And the nice thing about this, after you've done this, then the original problem, the instances of the original problem will become ground unsatisfiable. Yes. And if you can have a clauses, if you have a clauses like this, selection like this, then you propagate substitution back here. You obtain this set of clauses, but this part of this set of clauses would be already unsatisfiable at the ground level, and like Sato's SMT solver would detect, and it would need to select something else for the model. Good. So generally, this idea can be also, how to say, so results in a full calculus. Yes. So and general idea between previous calculus and this are similar. So we have first a set of first order clauses. We abstract and have ground abstraction now with equality. And here we apply. Now we need a solver module of equality. So like SMT solver, for example. But it will still give us selection of clauses such that in this ground model, these literals are true. Yes. So yeah, and if this SMT solver returns unsat, then our original problem is unsatisfied. final. Then what we need to do is we take a look at the literals in this model, and now we need to apply some more unit superposition and extract relevant instances from the proofs by this unit superposition. And add relevant instances to our set, of course. Okay. So what we showed, this procedure is somewhat incomplete, but it turned out to be, to implement it efficiently, it's very difficult to, so this reasoning should be done in the context of these clauses, yes. And this resulted in quite extensive work on constraints from this side. This is the slides which I omitted from the from this other talk, yes. So these constraints becomes quite big. We tried to different structures like BDDs and so on, but it resulted in first order BDDs which can be instantiated with these inferences and becomes pretty complicated. So nevertheless, it was implemented by Christoph Sticker. Yeah. So
Question, when you mention S&T solving, so are you saying you generate subproblems with equalities between propositional variables?
no, this is equational. So we start with equational problem, yes. We ground in the same way, just replacing all variables by some constant. It can be any ground term, yes. Doesn't matter for completeness. So if it's unsat, then it's unsat. If it's sat, we take a model equality, yes. This model nevertheless gives us selection of literals which are true in this model.
Oh, I see. So when you're grounding, if you have function symbols, you're actually including the function symbols.
Yes.
Treating them as uninterpreted.
Yes, yes,
Ah,
yes,
okay.
yes, yes. So they're included, they're not abstracted as literals, yes. So it's included, so this will be ground problem, equational problem, yes, that return to SAT solve. And here, this ground equational problem gives us a model, yes. We extract literals which are used, which are true in this model, and then we apply superposition to unabstracted version of this literals. Yes. So we are again abstracting back this constant back to variables, apply superposition, yes, and unit, but now unit superposition, and continue. Yeah. Extract the relevant instances, add these instances to our set of clauses. Yeah. So. It's still how to say, although we use superposition, this superposition is the unit superposition, yes. So it doesn't combine clauses, it doesn't. So at the end, it instantiates exactly the same original clauses, yes. So the clause length doesn't grow, it doesn't recombine clauses, and so on. So it has the same advantages as the original instantiation. Yeah. So. There's some experimental result. So iProve is written in OCaml, yes, and it has like 80,000, I guess, lines of code around like this. These results are actually not equational version, yes. So it's where the equality added axiomatic lecture. Okay. So this is effectively propositional fragment, which extension of propositional fragment, but where we have predicates, variables, but we don't have functional symbols other than constants. And it has many applications. Basically, it extends any SAT problem usually can be coded much more efficiently in this propositional EPR fragment. For example, Armin showed, and his colleagues showed, that bit vectors can be exponentially more succinctly encoded into this fragment. Yes. For example, QBF can be encoded, planning, and so on. So this is very versatile fragment. And I prove in bits 1 pair in this fragment, yes, which is currently the top theorem prover based on superposition. But nowadays it includes all other methods that known to human being, to humanity, yes, including instantiation. So yes, it implements everything that is known for first order reasoning. So it performs quite well for satisfiability problems, yes. So nitpick is a system
So
built
it's
by
actually
Jasmine.
mostly a lawyer or code in the first order case. So I mean, nitpick is translating higher order to first order, but in this case it's first order, so it's really cut.
So it's not your
Well,
performance, but Aloy's performance. Okay, so let's compare with Aloy. So it's let's shift the problem to Aloy. Yes. Anyways, so it has quite good performance on satisfiability, and CVC4 is a well-developed SMT solver which also has lots of satisfiability features for first-order reasoning. Yeah, so it's.
You're not giving us the timings, so is that the timeout or is it?
it's 5 minutes.
Time, 5 minutes general and average, like it's
Oh.
approximately the same for all solvers.
Have you tried to take union with E in the last line? Like how close would you get to vampire?
Sorry?
Have you tried to make a union of the problem solved by iPriver with the problem solved by E and compare it to the number of problems
Are
solved by
they
vampire?
solving disjoint sets of problems?
Yes. So okay, Vampire integrates everything like superposition, instantiation, specialized avatar for and so on. So it integrates lots of things. Yes. So it's difficult to compare that it is superposition, but superposition will be here. As superposition will not perform very well at all here. So
I
if
mean,
you take E, it will be
in
the
the
last.
last line, not in the middle line.
Well, E will be here. Yes.
No, the last line.
The last line. Last line E here because it's theorems here. So for proving theorems, first like superposition solvers are good, but if you compare Prover 9, who is by Bill McCune, who solved Robin's conjecture, yes, so it's equational theorem prover, and iProver still solves like 3 times more problems than Prover 9. Yes. And this is the version that doesn't integrate superposition. Yes. So this is the version with axiomatic quality, which is extremely surprising because general intuition that if you add axioms of equality, superposition solvers or resolution-based solvers will just die after that.
But I think the question was E
Does it
plus
solve?
iProver. The question I think was E plus iProver in the last line would be comparable to Vampire?
I don't know.
It would be below for sure, right? I mean, because Vampire almost solves a subset, a superset, sorry, of the others together, right? So just taking E and iProver together would
I don't know.
most likely not bring you above Vampire.
I don't know. It will add something.
Are there a
Definitely.
substantial number of problems that iProver solves and Vampire does not solve?
Yes, yes. So here, for example, but there were more.
in the last line.
No, last line includes these lines as well. So last line is just general.
No, but does iProver solve some
Yes.
problems that's different from what Vampire
Yes, yes, including problems coming from ITPs. Like there's a competition division from LTB, large theorem problems. There are some problems that iPro can only solve. But the dichotomy is bigger there. That Vampire solve much more problems there than iPro. But there are classes of problems even coming from just formalizations of mathematics.
For the first order set line, so is Vampire giving a saturated set of clauses? Or what is it?
It's a mixture, that's what I'm saying. So Vampire has superposition, instantiation that
But also
similar
finite
to
model finding.
iPro that
Okay.
was implemented.
So there could be many different kinds of.
Yes.
But it's mostly in finite models, right? So you
No.
implemented paradox.
Yeah, paradox as well. Yes.
Which is a finite model finder.
Yeah, yeah.
So at some
Paradox.
point they decided they were not really competing there, and 1 year they decided let's get more trophies, and then
Yes,
so-
because iPro was beating.
Okay. So it could be anything from a saturated set of clauses to like the output of MACE.
Yes,
Yeah,
yes,
okay.
yes, yes, indeed. But yeah, so now there's more solvers to compete. You need to combine it. So it's not against Vampire because it's a really powerful system, and if you want to compete, you need to integrate all these techniques.
And for first order SAT, what would an iProver output look like?
Okay, so it will give you definitional extension of the terminal. Okay, it's not time. I wanted to talk about something new, but this looks like a new.
That's okay, wait, sorry, take it.
Yes, but basically it's a definitional extension of term algebra, so you can say that P from P X if and only if and terms some equality, some first of the some fragment well, for X exists Y, and here is term equalities, yes, but these term equalities are interpreted in syntactically, yes, so in this absolute free term algebra. So this is decided basically. And it says P if and only if this holds. Okay, so
Show us offline, it's interesting. Show us an example offline afterwards.
Yes, yes. Okay.
Right, I think you're close to the end. And you still have a couple of minutes.
Okay, so this is the interesting part of the talk. Yeah, so this is joint. So it's not directly related to instantiation, but it's, I think, nice problems that are relevant to integrating these ATPs with ITPs. And the problem is that most problems coming from Sledgehammer and other applications, they have very many axioms, and very few of these axioms are actually used in the proof. And if you submit these axiomatizations, usually theorem proof just dies. So, but if you submit these relevant axioms, the proof can be quickly found. And so the problem is how we can select these relevant axioms. So there were several proposals and approaches, which is reasonably effective, but still, I think, not that effective. So first is based on syntactic or semantic structure of the problem. So basically, if you have a goal, we try to structurally understand what relevant axioms, like for example, which symbols occur in the goal and in the axioms, and so on. And another approach by Joseph Malaria, so based on machine learning, which is against some syntactic features encoded.
We also semantic.
Yeah, semantic and syntactic features, and then machine learning algorithms run through the existing proofs and try to learn if it gets a new goal, which would be the relevant axioms from that. Yes, and basically it has two phases, usually axiom selection and reasoning. What you want to combine that interaction being more intricate than that. So, and we have proposed that abstraction refinement approach. So we think that just selecting relevant axioms is a bit narrow view on the problem, yes. And the problem should be abstracted. And we have two abstractions, or approximation and approximation, and combination of these two abstractions. And there are some interesting relevant work on sound theorem proving, old work of play-state and speculative reasoning by Maria Polo and Leonardo and Chris Lynch. Yes, but they all a bit for different problems. They vary for very specific problems, and I think most of them didn't have like refinement or anything like this. And I think this is crucial for this type of problems. So our approach is to, if you have a problem which has lots of axioms, to partition this set of axioms into subsets, and each subset will be approximated by single axiom. So this in such a way that this axioms implies the whole subset. Okay? So if you have for example, this set of clauses, we can partition this into some subsets, and for each subset we just define one axiom, yes, and then axiom will imply, and since we're in causal logic, so for example, it will subsume all these clauses here, the subsets.
How do you pick the partition?
So yeah, so how to pick, I can't say in the, in the remaining time, but in causal logic you can see the common conditions, yes, and you can group them by common conditions and remove conditions that are outside of the intersection, for example. Yes. But there are many ways to do that. So after doing this, the problem reduced to much smaller problem, yes, because just each group represented by a single axiom. This axiom actually implies everything in this group. So we have this negated conjecture. Now this negated conjecture contradicts with these two axioms, yes. So now it's abstract axioms. And what we do, we look at the proof of this abstract proof, yes, which contains abstract axioms, and we refine these abstract axioms further. So which results in repartitioning this fragment, yes. Repartitioning further. So in this case, we just concretize, just choose concrete axioms. So if you apply next iteration, then that's it. So this would be already satisfiable. Note here that we didn't do anything from this with this part of the problem. So this part of the problem still remains abstract. Yes. And yeah, and this is the core of the procedure. So only that we focus only on the relevant, or refining only relevant parts of the axioms which actually occurs in the real proof or abstract proof. And here's the procedure. So basically what we do, we have concrete axioms, we obtain a set of abstract axioms, we run a theorem proof on these abstract axioms. This is much smaller or much compact set of axioms. And if it's sad, then the theorem is disproved because they imply our axioms. If it's unsad, then we need to refine the abstraction, but this refinement is based on the proof. So we only refine the abstract axioms that were current in the proof. Yes. And after this refinement, we continue. Yes. So these abstract axioms are removed and the refined version ended.
So in the previous picture, the left-hand side parts, you don't remove them because you might be using them later.
Yes, so we don't remove anything. Yes, we removed. So when we refined, we removed these abstract axioms and we replaced, in this case, by concrete ones. But we kept these ones. Yes, so it's always over approximation. Yes, it always implies our original set of formulas. Okay. And so this abstract proof can be concretized to concrete proof, so we don't need also, even when it's unsad, we can just replay this proof. That's it. We don't need to concretize this part. In both cases, sad or unsad. So this is
in the flow diagramming, SAT case, you may not know whether it's SAT or unsat in some reasonable amount of time, right? So
yeah.
So are you trying to pick approximations that are generally decidable?
Yes, so that's a good point. So it comes here. Yes. So for example, approximation, it can be decidable or not, but if you cannot prove SAT in a stronger system, yes, if you can't decide a much stronger system, then sort of might be less hope that you can do weak one. But yes, that's a very good point. So for example, we can replace non-variable terms by variables, yes, and we can reduce problems to the CPR fragment that is decidable. Yes. So we replace all terms by variables. We can remove literals, yes, and we can obtain stronger conditions, yes. Argument abstraction, so it's a bit of like second order abstractions where we, in many applications, we have predicates with like hundreds of arguments, yes. And with argument abstraction, we can abstract them with singular and so on arguments. And signature abstraction, where we collapse several signature symbols into one symbol. Okay? Yeah, so that's what I told, the subpartition of groups. And we, so the thing is that all reasoning is done either on abstract set of axioms or on the proof. Yes, so on the reduced set of axioms by the proof, restricted to the proof. Okay? And another side of the abstraction is under approximation, and under approximation is the other direction. And this is what current systems were, special case of what current systems are doing, like removing axioms or using ground instances or some instances of concrete axioms. Yes. So basically we construct a weaker set of weaker problems than our original problem. And now the reasoning is guided by models. So we have, before reasoning is guided by proofs, this reasoning is guided by models. So we have concrete axioms, we get abstract weaker set of axioms by, for example, removing some of the axioms. Yes. Now we run automated theorem proof. It can, yes, it doesn't need to be complete. And if it's unsad, then it's proved. Yes. If it's sad, it will return model of both negative conjecture and our axioms. And we refine abstraction by looking which axioms from concrete, for example, are contradicting our model. Yes. And if there is no such axioms, it is actually model of our real axioms. And if there is such axiom, we add it, yes, or concretize. And in this case, this model would not be repeated again, yes, because we sort of prohibit this model of repeating again. So this is under approximation. Yes, like removing instances, and And basically, to conclude, there is also combination, yes, where we combine both under and over approximation. So let me conclude the talk with challenges. And first order theorem problem is combination of specialized theory reasoning into first order theorem problem, which is long-standing challenge. Beta integration first order theorem problem with a SMT source. So there's some work and approaches for them presented here, and some other approaches like avatars that Anli, Voronov developing, and many others. But still, I think there is no perfect solution to this problem. And beta integration first order theorem problem is interactive theorem problem. So, for example, what would be, as we discussed here with several people, what would be good intermediate logic to communicate problems between first order theorem problem and interactive theorem problem. And problems of representations, like lots of, as Shankar coined this term, lots of problems lost in translations. If you incorrectly translate, naively translate a problem, usually it results into the resulting problem will be not solvable by, or very difficult to solve, whereas the original problem might be very easy to solve. And lots of this problem structure is lost in the translation. So I think there should be some chain of translators or communication between solvers. Thank you.
Questions?
So the last one, it reminded me Monty Newborn had this system called Octopus, where he was doing something similar, like he was strengthening the theory. The octopus was branching into the slaves, which each of them was strengthening the theory in various ways. And if the strengthened theory found the proof, you would use it for guidance of the original theory to get the proof.
So I don't know this one.
I
So
competed last time, before 2010.
I might miss it. Yeah, but our goal was to make like clean framework how we can do such things.
It's also similar, like for example, what Verov is doing with this thing.
Yeah, but there are lots of things, but they're very specific for very specific problems designed. Usually they don't have like an abstraction refinement loop. Yes.
Yeah,
it's not clear. Yes. So I think it's good to formulate it in some uniform framework and then partition problems like how to partition towards the abstraction and so on.
So this the abstraction refinement thing could be applied to just about anything, right? You could take CDCL and apply it to it. I mean, you could drop axioms, drop clauses.
Yes, definitely. Yeah, it's not restricted to first order or any particular.
And similarly, going back to the instantiation proving loop, you could treat the thing where you do the grounding and literal selection. You could treat that as an oracle. Right? You could have other procedures than SAT.
Yes, that's what I mean. With the quality like SMT, and in principle you can extend it. So we also have a paper to extend it with other theories. Yes. So the requirement of the theory is that you need to have reasoning, complete reasoning with unit literals. Yes. And basically, if you produce, basically it's resulting in like E unifier. Yes. If you can do E unification, then you can use these E unifiers to instantiate.
So I was wondering if you could do these things in parallel, so that you could call many different oracles with many different abstractions. And,
that's a good idea. I don't know. No, it could be a good idea. The problem is that you need to merge these models. Yes. Different abstractions will give you different models, because you want to instantiate all of them. So here's the beauty is that you can guide it by one model, so you restrict your inferences. Yes. If you have several models, you either need to combine this to one model, or you need to instantiate in both models, yes, which sort of can be prolific.
does it mean, can you get some kind of, by doing this, can you get some kind of an activity heuristic, so that you can look at things that are more active.
Yes,
sources on
that's a
the
good idea. Yes. Yeah. The thing is that you need something good. Yeah. So the thing is that now we treat the SATSOL as a black box, like mainly. So I try to add some more like heuristic type guidance to SATSOL as well, because from SATSOL every literal is the same. Yes. Whereas from the first order point of view, one literal can be very prolific, and another literal can be like made like it's already ground. Yes. Yes. So SATSOL might not know the difference. So that's
Okay, Joseph again.
I basically had a similar question, like whether you had done any research, like in guiding, in telling the subsolver, in guiding the subsolver in producing good counter models.
I did it for like model checking problems, for example. So I have this notion of soft assumptions. Yes. So when you assume literal to SATSolver in this assumption, like many SATSolvers allow you to assume literal. Yes. And soft assumptions means that if the model doesn't satisfy, just remove one by one them until it becomes a model. So you don't care about them that much in terms of guidance. So I'll try to do that for model checking. Yeah. But again, so such things need to be experimented a lot and so on. It takes time.
I'm just wondering whether you can, for example, state a simple heuristic which tells you like this counter model is better than this counter model. Whether you can have some very like simple heuristic, like minimizing the number of true assignments or minimizing the number of false assignments, or like what are your heuristics for choosing a counter model if you had this non-determinism?
So heuristic, the main heuristic is that it shouldn't be different from previous models.
Yeah, I know
this is
yes,
and this is important because in this loop, if model changes, all first order reasons need to be redundant. So this is the main sort of heuristic. But there are other heuristics, like I said, in model checking, I try to define what is an important literal and so on, what literals I want to be true as much as possible. But this is again, it's might be the approach like on the frequency, or like CDCL, they have all this variable selection and so on. Dynamic variable selection is more reasonable, but I didn't get into it.
We looked at taking problems that are known to be unsat and trying to find the unsat core through abstraction rather than looking at the proof.
Unsat core?
Just by using abstraction, these are things that you know are unsat, but you don't know which subset of these is unsat.
So in proof reconstruction, I do unsat cores.
Right.
So
but without doing proof reconstruction, can you use a more kind of like an abstraction-based technique to?
Yeah. So in this abstraction, so I use these proofs. Yes, in over approximation, when I refine, I get unsat core, and I refine all the things inside core until it becomes sat. And if it's refined to the ground, not to the ground, to the original clauses, then original clauses, this part is already unsat. And if it returns sat at some point, yes, then this part of clauses is sat with conjecture. So I pick more, replace the subscript with this set, and we continue.
Are you sure that gives you an unsat core on the original clauses?
Yeah, if it's unsat at the ground level, yes, it's unsat at the original clause. I can trace.
No, does it give you the minimal unsat core?
Minimal. I'm not that bothered with minimality. I just bothered with sub-minimal in the sense that clause that occurs in the proof. Yes. So SATSolver returns me unsat core. Yes, and I try to minimize it, but usually it's quite expensive. It doesn't pay off.
Okay. So thanks a lot.